Okay, let's get started. Hello, everyone, and thank you for joining our webinar. Unsupervised machine learning is essential for fraud detection. We know you're very busy. There are many ways you could be spending the next hour, so we're very flattered that you've chosen to spend that time with us. We hope you find this webinar to be interesting and informative. Next slide. My name is David Ronald, and I'll be your host today. I am a Senior Director of Product Marketing at DataVisor, and I have the privilege of introducing your presenter, Fong Yu. Fong co-founded DataVisor after seeing the need for better methods for detecting and managing risk within the financial services industry. In her role as Chief Product Officer, Fong is responsible for DataVisor's strategic product direction. Prior to founding DataVisor, Fong spent 8 years at Microsoft Research, developing big data algorithms and systems for identifying various ways of protecting against malicious traffic. Fong has a PhD in computer science from the University of California at Berkeley. She's brilliant, need I say that? And a bachelor's degree in computer science from Fudan University. In her spare time, Fong tells me that she enjoys traveling to unusual places and eating interesting cuisines. Next slide. So here are a couple of housekeeping issues. Of course, we hope this webinar will be interactive. Don't be shy. Don't wait till the end to submit your questions. We'd love for you to submit questions, during the webinar. And if that's the case, then we'll answer questions more or less as they come in. And the best way to submit questions is through the Q&A panel at the bottom of the Zoom panel. If you do have any technical issues, let us know, and the best way to do that is using chat. Next slide. So here is the introduction here is today's agenda. I'll begin with a brief introduction to DataVisor, and then I'll pass things over to Fong. And Fong will look at, why unsupervised machine learning is essential for fraud detection. Next, why and how can fraudsters launch large-scale attacks quickly? And third would be when to choose unsupervised machine learning. And then we'll leave some time at the end for a Q&A. Next slide. So in his 2022 report, The Buyer's Guide for Fraud Detection in Banking, Gartner analyst Akif Khan, who many of you may know, said, the strategic imperative is to implement a customer-centric approach to fraud detection, monitoring transactions and events across products and channels on a single platform. DataVisor is a single comprehensive platform for fraud and risk. Let's look at that. Next slide, please. DataVisor enables you to make the best fraud decisions in real time, every time. Now, that's a very bold claim. How do we enable you to do that? Well, there are many ways, but they sort of fall into three big buckets. The first one is fast detection. The second one is best results. And the third is comprehensive functions. And when I say fast detection, I'm referring to real-time data orchestration and decisioning with ultra-low end-to-end latency. When I say best results, I'm referring to cutting-edge unsupervised machine learning, the topic of today's webinar, that catches new and unknown types of fraud, and powerful decision workflows that enable you to build the best detection strategies. And when I say comprehensive functions, I'm referring to a broad suite of modules to support account lifecycle protection across multiple use cases. Next slide. So DataVisor is a single platform that supports multiple use cases. There are many use cases. Somebody recently told me there's over 16 use cases we support, but here are probably the 5 most popular ones: application fraud, transaction fraud, debit, credit, payment fraud, account takeover protection, and money laundering. Next slide. So let me tee up Fong without any further ado. I found this quote from IT Novarica, a very well-respected analyst firm in our industry. This quote comes from a report called Fraud and AML Machine Learning Platforms, Financial Crime Detection's Next Frontier, from August of 2021. Really excellent report. If you haven't had an opportunity to read it, I recommend that you do. And this quote says, "Those that do not invest in machine learning risk being left behind, as it provides superior customer experiences while mitigating fraud." So with that, let me pass things over to Phong.
Thank you, David. So let's start talking about unsupervised machine learning. Before we actually get into the details, let me actually show you a real-world examples of how the attack conducted. So this is an anonymized example, but it's actually happening in the real world. So if you look at the transactions here, so we have a bunch of transactions coming in from different IP address. Some of them are ACH transferred, some of them are credit card transaction sending to different senders and receivers and different amount. So if we look at all of these transactions, individually, they actually all look legitimate. So there's nothing wrong with these transactions when at the first glance. But if we organize the information slightly different, patterns start to show. So you can see every customer here has exactly 2 transactions. They are 2 days gap. That they actually use the same IP address for the same transactions, but they all follow the pattern. They first have a canceled ACH transfer, then they actually have a credit card transaction. The sender and the person is actually the same, but the receiver, you can see the first actually sending to a random receiver. Then the second receiver, although the names are different, but if you look at except the middle name, the first name and the last name are the same. So this is actually one of the examples that showing the attackers in this case controlled 3 customer accounts. And they know this pattern can follow through, slip through the existing systems because they first establish ACH transfer so that they, this is actually a known account with some transfers, especially ACH, can redeem a little bit at a lower risk than the credit card transactions. So they use that to establish their presence, and then they follow the credit card transactions. So you can see using this pattern, they test it and it's able to work. So they conduct a large scale attack in this. So the actual scale of this attack is far more than 3, but here we use 3 as an illustration. So using, if we focusing on these transactions individually, we won't see this pattern. But if we zoom out and looking at each accounts, multiple transactions over their lifetime, and more importantly, looking at the correlations about from different customers, then we see the patterns. So using this approach, the unsupervised machine learning can capture this pattern and deny all of these transfers. So this is actually why unsupervised machine learning is important. As you can see, these patterns actually can change. So today they use credit card transactions at 680 degrees, around $680 around that range. But tomorrow they can actually conduct even smaller, like 500 or even 200. But they can involve a large number of accounts. Today they use credit card. Tomorrow they actually may use other transfer methods. So when we have this type of attack, you can see that the attacker can, because they can control large number of accounts, they can launch large-scale attacks. If we rely on the traditional rule system or supervised machine learning systems, because those systems rely on labels. So we have to have a loss and see what is the pattern. Then we start putting rules and training the model. In that case, because the label collection in many cases needs to take months to have the model mature. In most cases, we need to wait 3 months. And even we develop the model training super quickly with the label within 1 day, we develop a model that's still already 3 months old. And after we going through the model governance, implementation, pushing into the production, it can be well 3 to 6 months. So there's a large exposure to all of these new patterns of attacks. But using unsupervised machine learning, we are able to detect the fraud patterns at the day one when they start actually informing. And then also when they change, we are able to detect that as well. So that's why we help large customers to shorten the 3 to 6 months of a gap in real-time detection of the new fraud patterns, and effectively can reduce a fraud loss by another 20 to 40%. So this is one example. You may wonder, how large are such attacks, right? Whether I would be subject to such attack, if it happen once in a while, or it's happening every day. So next, I'm going to show you why attackers are able to launch these large-scale attacks quickly, and how large are these attacks, and how did they conduct it. So we need to understand attackers to better defend it. So today, attackers actually have a lot of tools to help them conduct all kinds of fraud attack or money laundering attacks. So if you see, they can actually hire cheap labor, mechanical turks. They can register fake merchant. We see a lot of fake merchant register this way just to deplete the credit cards, or they actually have buyer-seller collusions. They can have a lot of stolen identities. There are data breaches all the time. And then, so all of our information is actually at the fraudsters and attackers' hand. And then moreover, beyond the stolen identities, they also have already created over years, millions of synthetic IDs. So there are large amount of synthetic IDs actually created years and years ago, and they even go back to 10 years. These IDs are already matured, and they have applied for different credit card, bankings. They just apply those and they sit on that. So these actually are no longer a thin profile, but they actually have histories. And then these are actually at a fraudster's hand that they can launch attacks at any time using these synthetic identities. And of course, they can take over the borrowed identities of the seniors, of the new immigrants, of the newborns, and they have all of these. So they actually essentially can take over a lot of these accounts. And then they are also very good at hiding their trails. For example, they can have a cloud infrastructure having different IP address. They have mobile device flashing. They can have new devices. They have emulators to simulate multiple devices. I will show you just using the desktop. And they also have a proxy and VPNs. They can even bypass SMS verifications. As a result, we see the attack pattern really change very, very rapidly. So if you look at IP address, from our years of work looking at over 4 billion user accounts, the fraudsters, when they conduct the attack, 65% of IP address are used for 7 days or fewer. So if we rely on the blacklist approach, the shelf life of those blacklists are pretty low. And then the worst part is that many IPs actually are shared. They can be public IP address. They can be mobile ranges. There are a lot of good users behind it. If we keep blocking it, first, it's actually always late. Second, we may actually hurt a lot of good users. Similar things apply for device IDs. They're able to do device flashing or emulators. So many of the device IDs actually change very quickly as well, especially if we don't have a good way to fingerprint the devices. And even email domains are actually quite easy to obtain. The fraudsters use stolen credit cards to actually register new email domain quickly, conduct the attack, and dispose those. So 52% of the email domain are used 7 days or fewer. So with all these tools, and also this kind of like a large scale attack method, some of the old days, you see a lot of like the picture like these, we have a human actually operating all of these like a brick of walls of the devices to conduct attack. But nowadays, they don't actually need to even have a human behind it. They can actually have a software controls many of these virtual devices, simulated them, remote control them. They can do the phishing, they can do the scanning, they can pretend to be good users. So these are all allow them to launch attack at scale. As a result, you can see, we really see a lot of actually coordinated fraud attack by these professional fraudsters. If you look at the social sectors, for example, fraudulent social account opening, email account opening, when they actually do scamming and phishing, these cases, the profit of the account is less than 10 cents and sometimes even a fraction of a cent, because they need to send a large amount of scams, large amount of the emails, phishing to actually really get somebody reply to them. So the attack campaign size that we capture is usually the more than 100 or sometimes to the millions of attack scales. So it's really large because each account gives them very little financial gain. For the e-commerce sector, when you actually do the transactions, then each account, sometimes they can tens of dollars and often they can get hundreds of dollars. So the attack is actually usually smaller. It can be tens to, or sometimes it can be thousand. It's very prominent in those promotion abuse when we actually give out promotion for somebody to actually, for example, new customer registration, etc. Unfortunately, we see from in the wild that often more than 90% of the promotion, if the promotion is open to the public, goes into the fraudster's hand, because they can register many accounts using bots very quickly to deplete the money. So all the promotion dollar end up actually wasted. And of course, account takeover is also a big source for all of these attacks as well. And then even with the transaction, 40 to 50% of the attacks are conducted by these professional fraudsters. In the financial sectors for FIs, for the credit card and banking account opening fraud, there are first-party fraud, of course, and then there are but they are more like I would say synthetic IDs and third-party fraud, and all those actually colluded fraud. And I applied for credit card, and I know this is not working for me, so I actually use my friends and family members. So they register a bunch of these cards. So the portion of the coordinated fraud is like 40 to 50%. For the account takeover, of course, it's higher, and the transaction fraud, depending on the sectors. Some of the a small ice cream shop, they probably don't experience much of the coordinated fraud at all because it's very local. But if for someone that's online, especially selling very easy to resell digital goods, or actually the items have a lot of resale values, or it's like a live cash goods, then those are actually subject to heavy attacks. So the profit of one count can easily go up to more than 1,000. And the attack campaign side can also be much smaller, vary from 2 to, we also see financial sector with more than 1,000 accounts conducted by the same fraudsters as well. So this actually really show there are a bunch of attacks there, and we really need to prepare ourselves to fight against all kinds of these attacks. Now, next, I want to talk about how to use different type of machine learning algorithm to combat against these attacks. So if you have questions, please feel free to put it in right now, and then we can always answer a question as I talk. So there are different types of fraud detection method out there. So as all of you must be super familiar with the blacklist approach, the rules engine, the abnormality detection, the supervised and unsupervised. So I'll go a little bit like deep into each one, but in terms of the complexity, blacklist, whitelist is definitely the most easy to implement. You put something, you whitelist particular user, you blacklist particular IP address, particular merchant. So these are actually very, very easy to put into. Okay, we have one question. And then abnormal detection is a little bit like harder because you actually need to put in your abnormally functions. And the rules engines always need to maintain, you need to come up with new rules. Supervised machine learning is a little bit more complex than rules engine because it involves model training, model governance, etc. And unsupervised machine learning, of course, is most complex. In terms of a new attack detections, right? Blacklist, whitelist, and the rules engine are more reactive. So it's not necessarily able to detect new attacks very well. Abnormality detection, on the other hand, is relatively better, but it's not very precise. For supervised machine learning, because it's able to train the model, so it's not exactly as a rule, it's able to detect some of the new attacks, but it's mostly based on the past behavior. For supervised machine learning, it is actually the best in terms of the detection of the new attacks because it's not rely on label and it's beautiful. So next, let's go a little bit deeper into the different methods. So if you look at the reputation, it's the white and the blacklist. So the examples are commonly used like emails, IP address, device, credit card number, usually put into sometimes a whitelist when you travel. You would call the credit card company, I'm going to travel, so they will roughly put us into a whitelist for next few days into a specific destination, and then phone numbers as well. So the problem of this approach is that it's very reactive. It works decently for these kind of like credit cards, etc. But for IP address, as I mentioned, it will have a very high false positive rate because there are a lot of sharing of the IP address. And then we sometimes see even like some countries, they have a national proxies. And then we also see a lot of like airport IP, Starbucks IPs, etc. And nowadays, we can not even always block the cloud IP because people may think, oh, I see IP address from Amazon, and then most likely it's actually by somebody like a fraudster setting up like not necessarily Amazon, but all the cloud service or the cloud service IP address, I should block it. But it's actually today, this is very risky because there are a lot of like a legitimate proxy set up on the cloud services. And then for some of even the web browser, for the safe protection mode, they also redirect traffic into the cloud to scan it and then redirect out. So you will see many legitimate traffic actually coming from those cloud services and cannot easily block those because they actually do have quite a lot of good users behind it. So this approach, blacklist, whitelist, is usually the quickest way. If you see something, you quickly put it in, but it need to be very carefully evaluated for them, especially take it out after the attack actually wave goes away. Similars actually apply to the rules and the scorecard. For rules and the scorecard, the two things are actually very connected. So what are the rules? Rules are a bunch of logics. So there's a rule conditions. For example, if the billing address is not equal to the shipping address and the merchant is new to the card, we can send the transaction to a manual review. This is a very simple strategy. So it has a condition, and then there's also performing actions. For the scorecard, it's a bunch of the rules. So because rules, you kind of each rule have some like a decision already, but usually it's in reality there are much of different reasons. For example, here is a simple scorecard. If the IP address is an anonymous proxy, then we add some weight. If the account is actually a very good account, I know this is a legitimate user, I actually minus some weight. And then if the email is actually also legitimate, I also minus. If there's a mismatch of the billing country IP address, so I added to it. So it's kind of overall, the scorecard is a little bit like a small manual machine learning models. So you put all the conditions, all the different weights. In the end, it will decide precisely based on your weight and give you reasons why this is actually blocked or approved, and based on these weights. So it's very easy to explain and understand for both the rules and the scorecard. But again, this is actually a little bit more reactive. So it's for people to come up with these rules or scorecards, usually based on the loss experience or the past experience. So it need to be very carefully put in. And then also there's a lot of like false positives associated with these because when there's attack, for example, we see the attack coming from this particular type of devices and from this particular channel, and then purchase this type of items. When we see such attacks, people will put in the rule, if it's coming from this channel, this particular behavior, I block. There's nothing wrong about that approach. During that day, the accuracy of the rule could be 99% because there are a lot of fraud attacks actually happening that day. But when the attacker sees, oh, you block my like channel, you block my pattern, and naturally they will evolve, right? They will change to a different channel, they will change to different pattern. Then a few days later, this rule can be 99% false positives because they could be actually still legitimate users actually still using those channels. So in that way, the accuracy of a rule can have a huge drop in precisions very quickly. For these type of the rules, we need to be very, very carefully monitor its performance. When the performance is not there anymore, we need to actually deprecate the rules or have more robust rules to replace those kind of quick reaction rules. Next,
Fong, if I can jump in, there's a question. Sorry to interrupt. This question came in through chat, and the question was: we are using blacklists today. What type of improvement will UML provide?
Yeah, so the blacklist, I'll give examples today. So the blacklist is pretty reactive, right? You need to manually put into the blacklist. What the unsupervised machine learning will do is automatically discover those patterns. So essentially kind of automatically managing the blacklist for you on top of, so if there is actually new IP address coming up, if there is actually a new device coming up, you don't need to worry that you need to maintain, you put that into the blacklist. The unsupervised machine learning will capture that pattern and automatically flag the items from those IP address for you. As a matter of fact, I was just actually looking at the recent attack actually happening 2 days ago. Someone actually, I think a fraudster took over a legitimate like a chocolate website, and it ring a lot of us stolen credit card actually through it. When you actually looking at those, right, this is actually a perfect example that for that chocolate website, it is actually a legitimate website, but there are legitimate users, very small portion of the legitimate users actually going through. When the attack goes, especially those actually testing credit cards, those actually can go very big, like tens of thousands of transactions per day. But the website still have like quite some good traffic every day. So if you put that into the blacklist, that poor merchant will all of a sudden actually lost all its traffic. And if you put the rule, it's the same thing. But all the legitimate users will got hurt. But if for the unsupervised machine learning, because it's looking at the correlations, it is able to see this, all of these actually having the same patterns. And I'm able to separate, it did a very, very good job, separate the legitimate traffic versus actually those bot traffic apart, and only detecting those a large amount of traffic to this the chocolate website as a fraud versus actually letting the legitimate traffic go through.
Terrific. Thank you.
Thank you for the question. Next, I actually will move into the supervised machine learning. So supervised machine learning is a little bit better than the rules in terms of you don't have humans to really, because the rule writing, how do you define the weight? Like it's actually pretty hard. It really based on a lot of the analysts need to manually think and try so that they have pivot table, etc., to define the threshold. So this is a lot of like a manual intensive work. But what supervised machine learning does is automatically do this. So you gave it the labels, the good versus bad, and then and also the past transactions, and tell the machine, hey, give me a model so that you can automatically do it for me, and giving a new transaction, tell me this is good or bad. So it will create this is a kind of like a logistic regression, right? So it will create a model similar to this, depending on the algorithms you actually do. So essentially, you will put different data points, and a good or bad, and trying to find a boundary to separate these things. It can be actually hyperdimensional space. It can be actually linear space. So there are a lot of supervised machine learning algorithms there. And then they are actually effectively finding the boundaries between the good and the bad. And they came up with automatic way of detecting. So that's actually much more efficient than the manual analyst to actually figure out what is the threshold to maintain a large rule sets, actually to see this is all the scorecard. The drawback of this is actually it needs labels. And then depending on the label, some of the labels actually come pretty quickly. For example, if there's a account takeover, some users actually find it pretty quickly, they will report. Some of the chargebacks, some of the labels will come in a few weeks as well. But there are certain things that like chargeback label can come from a few days to several months. And then like loan applications, right? You will not know whether the loan is good or bad until they don't pay back the first month's bill, or more effectively second month, because first month many people have technical difficulties or lost an email, they don't pay back, but the second month. So effectively, you need to wait 2 months to actually get the label. That's why there's always a gap of a delay in terms of a supervised machine learning. So that's why the unsupervised machine learning really help. So before going to unsupervised, there's also anomaly detection many people use. It's relatively less used for fraud, but it's so heavily used in security. So when essentially it's finding the abnormals. So for example, you have data points, what if there's abnormals? So you capture these things. When there's actually a spike or dip, that you know there's obviously something wrong, especially at this dip. Of course, sometimes there's a data missing or there's engineering issues. But when you actually have spikes, this is usually actually related to fraud. And then, but the problem of this approach is that when you have a spike, like the chocolate site example that I mentioned, it's not necessarily everything on that is fraud. So you still need to actually, within that spike, to distinguish the good versus bad. And there's also collective abnormality. You're finding a collection of the things that's actually coming out of an abnormal. So this is the abnormality detection. We see it relatively fewer used for fraud detection unless you actually employ a lot of manual review. Because for security, you really want to capture everything. You cannot let anything go, attack go through. So they employ a lot of like a manual review. They have a lot of alerts. But for fraud detections, if you employ a lot of the manual reviews, first actually hurt good user experience. If we actually just blindly, all of us got annoyed if our credit card actually didn't go through, then maybe actually just use another credit card. The credit card company may actually lose the client forever if there are actually a few of those incidents happen. So the client user experience also matters a lot. You cannot delay the transaction. And then also because of these abnormally high false positives, the the amount of the manual review is also prohibitive. So we cannot have so many manual reviews to actually looking at all the transactions and yet finding a lot of false positives. That's why pure approach of abnormally, just saying this is abnormal, is relatively less used in the fraud domain, because there are always people, because people follow a long tail distribution, right? There are always people actually doing a little bit abnormal things. You cannot say somebody get up in the middle of the night, have a large wire into the foreign country. That's a fraudster, because people do have things coming up. And then now we're actually moving to the unsupervised machine learning. Well known, there are two types of unsupervised machine learning. One is a clustering method. The other actually is graph analysis. Both are actually pretty efficient in terms of finding something suspicious. So, for example, for the clustering approach, right? Well known, for example, DB scam, K-mean, etc. So the K-mean algorithm is efficient, but it's very hard to actually pick a K. You don't know how many clusters are there. And then also, there's not necessarily all the users actually are within the clusters are bad. There are many actually good users. So the clustering approach really putting people into the clusters. And as we mentioned, the fraudsters, because their behaviors and the fraudster account, if they are controlled by fraudsters, they are kind of like remote control, they follow the same script. Their behavior is actually very similar. So they will naturally cluster in terms of their behavior. But the challenging is really, how do you actually know how many cases are there? How do you do real-time clustering, finding the suspicious subclusters? How do you separate it from the rest of the normal user? Because in many cases, 99% of the transactions are okay. So how to really separate that to a real-time algorithm is challenging. The graph analysis is also very, very important, because similar like clustering, they have a lot of like sharing patterns, right? Sharing IP address, sharing the device, or if they do very well, they do distributed, but they're sharing the behavior patterns. So how to build the graph, finding the correlation is also one of the key points, and also doing it in the real time. So what DataVisor do is actually really merge the clustering approach with the graph analysis. So what we do is that, so I use this the paint. So this is a pointillism paintings. If you look at each one, it's a dot, right? It's like, I would say this is like a count. You cannot say this is a red, or this red dot means anything if you really actually into that dot. But if you zoom out, then you actually start to seeing the patterns. Or this part of the dark dot actually represents hair. This set of the dark dot represents eye, and this set of dark dots represent mouth. So it really get the picture when we actually zoom out. That's the essence of unsupervised machine learning, that how we actually maintain the big picture. We want to see the correlations, but we also want to see the big picture, where they are, so that we can say this is good versus bad. So next,
Fong, if I can jump in, there's been another question. The question is, machine learning models need to be retrained. How often does DataVisor recommend retraining the model?
Oh, so that I will actually go a little bit at the end. I will answer that after I explain the unsupervised machine learning. So then for supervised machine learning, you typically need to retrain it quite often. I think the industry standard that for the banks, it actually varies from months to years, because each model needs to go through the manual governance. So that cycle you cannot retrain it every day, because there's no way that you actually go through that model governance process. For commerce, they're actually not subject to those like heavy model governance. There's actually a way to actually retrain it every hour, every day, based on the label. So there could be new like ways to set up the automated retraining when we get the label. But for unsupervised machine learning, because it's unsupervised, it's not actually based on a label. So actually it doesn't need to be retrained often. So we have models actually running for months, for years, very nicely, don't decay much. You don't have to retrain it because there's no label feeding to it. Okay, so next few slides is probably 3 slides, a little bit technical. That's only 3 technical slides, but feel free to answer questions. So I will try to explain it in a little bit like a high level way. So in the traditional supervised machine learning, you actually see that there's transactions, but we are deciding based on that transaction alone. So back to the picture here, if the transaction is a dot, we are based on that dot alone to actually decide on these transactions. We may actually use this transactions called history, the merchant's history information, the digital information, but still, when we are actually making the decision, we are making the decision based on the transaction alone. That's why it can be very much parallelized. You can have decide multiple transactions in parallel. On data advisors, supervised machine learning, on the other hand, is actually very different. It's not deciding just based on the transaction. It's also based to try zoom out and try to see where it's actually focused on and looking at all the correlated transactions together in that, for example, in the past one, it was looking at the correlations in terms of neighborhood, in terms of all the like the colors, or where are all the black colors, where are the shape of the dots. So it's running a lot of correlations. In the real world, this type of correlation can be digital informations. For example, when they are sharing IPs or device, that's very, very straightforward. They can be actually behavior patterns. The set of merchant, this card actually went to pass with the pass sequence of the merchant, like the previously, the sequence of the buying pattern, ACH after the credit card transaction, the amount, the currency, the order, the timings, and then the geolocation, all the IP jumping histories. And if there's any like user generated comments, for example, there's when we do money transfers, there's actually a comment. Those can all be utilized to form the correlations. So it's really not trying to decide just based on these transactions, but it's based on deciding all the correlated ones to see where there's a strong pattern of correlations. Because in our previous example, because these fraudsters control many of these accounts, and they actually really kind of following this like instructions, their patterns are very correlated. So we will try to find all these correlations. It's also very, very good in terms of new and missing values, especially in terms of the digital signals. In the supervised machine learning case, for example, IP address, right? IP address can have millions of values. And then because it's so many, right? So what the supervised machine learning will do is kind of like remembering top good and top bad. I know this IP address, this few IP address in the past, they always send me good traffic. I remember these are good ones. And these few actually have send me bad traffic. I remember those. For a large amount, I never see anything, or they actually send me regular traffic, then good and bad, and then I don't know much. But that approach really is not effective because, as we mentioned, IP address change very quickly. What you remember based on history of 3 months ago, it doesn't apply today. And then moreover, in many cases, for example, the browser agent, right? iPhone can have a new device actually push out with a brand new browser agent, new device type, and a new device ID, the new value coming up all the time. So really what we need to do is not only focusing on the memory of the past, well, we actually need to take in all the values and even the new values, really to looking at the correlations of these values and see whether there are suspicious activities happening on these any of these values. So in this way, the unsupervised machine learning is very, very good even we have partially missing data. It's also very good at the new data coming up because there's no memory. So I for any new devices, new payment merchant coming up, I can always analyze in the same way that I know how to analyze like known ones before. So this really not only that we don't need to retrain the model very often due to the new labels, but it's also very good for apply to the new country. We actually, our client utilize us a lot when they actually expand network into different country, they employ new merchant, or they actually develop new product. For example, there are a lot of interest in unsupervised machine learning when people actually move into RTP, the kind of a new payment rail that they don't have much labels, and then this is brand new kind of product to them, but real-time payment can be subject to real-time fraud. That's why there are a lot of interest in using unsupervised machine learning to solve those problems. And we see quite a lot of success in that. So a little bit like summarize in terms of different approaches. When you don't have labels, then you can only use unsupervised machine learning, or you actually have unsupervised machine learning generate some labels. Then you can use a combination of a supervised and unsupervised machine learning. When you have partial or delayed labels, then the supervised machine learning doesn't work super well because it will miss all those new patterns. But unsupervised machine learning, as we said, because it's able to capture things on the fly, it works pretty good. And then it also works perfectly with the supervised plus unsupervised machine learning. When we have four labels, of course, the supervised machine learning works very well, but it's except for the new patterns. Unsupervised machine learning works also, and then combination also works very well. And then we conducted analysis. If we have 55% of the label missing, unsupervised machine learning is actually able to capture the missing label very well and have very high precision. Even 50% of the label missing is okay. So it's really when we have partial labels, like the chargeback, when we start to having some signals coming in, not only the unsupervised machine learning can capture the new fraud pattern, but I can also using that to augment the labels for the supervised machine learning to train much faster. So let's put this supervised machine learning, unsupervised machine learning in the real world. How different attacks can be captured using these two methods. So if you look at the new account registration for this, is like, for example, credit card application, loan application, digital wallet application, these kind of new registrations. So in the new registration, if it's a very, very large provider, then you probably will have a lot of attacks. But let's actually assume we have a median kind of provider. So this is kind of like a typical behavior we see from our clients. So within the months, like a year, so there are always going to be a lot of like first-party fraud patterns. So those actually people apply for a credit card but never want to pay back. So this is kind of a baseline. For these baseline behavior fraud, it can be captured pretty well using the rules or supervised machine learning. There are a small portion of like coordinated fraud. That's usually quite small. For example, somebody in some region, they figure, oh, I apply for this credit card and I can do this way to get it. And then I actually use my brother's phone number, information. I use encourage all my family members or friends to apply for the same credit card. So they will be actually a little bit like localized coordinated fraud, or they actually sometimes use their own social security, but they actually manipulated their own information a little bit. So these kind of small scale coordinated fraud and the repeated manual efforts for the friends and family, it can be actually captured by unsupervised machine learning or the linkage analysis. So we can capture those pretty well. For the large scale ones, from time to time, it may not be every single month they experience, but from time to time, they will experience like this wave of attacks. It can be from third-party fraud because of identity leak. we see the clients actually, for example, they target 600, 700 credit range, but all of a sudden they have a lot of 700 plus applications coming in. And they thought those were actually very good ones, but end up all being fraud. So these are more like third-party fraud attacks. And then also synthetic IDs, because as mentioned, there are a lot of synthetic ID already there, incubated, no longer a sync profile, so they can actually apply for these credit cards and conduct the bust out of fraud. So what we use unsupervised machine learning day to day is actually to capture these small scaled localized attack, and then more important to prevent all of these large scale attack, because when these actually happen, the volume is actually far more than the average baseline. For transaction fraud, on the other hand, it's a little bit more than the application fraud because volume is higher. Each account have many transactions. So for especially for the large players, the amount of the coordinate fraud. So here you can still see waves. Here the waves every day. So they are like different type of coordinate fraud. And then this is a large network that we see. So if you see the transaction fraud and the baseline, the supervised machine learning can probably capture a good portion of it. Just you keep training and then retraining, but there are a good portion of it, as we mentioned, around like 40 or 50% of them are actually conducted by professional attackers. The supervised machine learning can capture some of them, but we'll miss some other portion. Combining supervised with unsupervised really actually capture the whole attack way, no matter it's a individual conducted ones or the coordinated fraud. So as we mentioned here, supervised and the rules are very good at known patterns. And then unsupervised machine learning is very good at detecting the coordinated patterns by those professional attackers. Okay, so this is the last slide of my talk. And then this is kind of like a conclusion for the technology recommendation. Today, we talked many algorithms. We talk about the rules. We talk about the supervised machine learning. We talk about unsupervised machine learning. We also talk about the scorecard and also putting everything together using ensemble way. As a takeaway, rules, I think we need all of these in the as a suite of a defense method to come back against today's advanced fraud patterns. For rules, because no models are perfect, so that you cannot actually get a model 100%. There will always be cases you actually want to put strategy into it. So rules is still actually very effective when you actually want to put in some ad hoc or they actually put in some new strategies, because model development needs time for both supervised and unsupervised machine learning. You cannot change the model within 5 minutes, but you can put in the rule within a couple of minutes. So the rule is still a kind of, in many cases, a baseline. And if there's anything you need to adjust, especially when we have like a decision for you want to build a segmentation, this segment of traffic using this type of machine learning models, this type of strategy, that segment using that other strategy. Good user use one strategy, new user use another set of strategy. Rules actually are very good in terms of putting those strategies in place and then to combine with the decision flow, so that you can say this sector using this criteria, you split the traffic. The only careful way that we need to actually do is essentially monitor the rule performance. As I mentioned, the rules can be very effective in one day, and tomorrow when the attack the rule can be actually capturing a lot of false positives. So automated monitoring the rules performance and automatic adjust the thresholds, and then knowing the rule is no longer perfect or selecting a better threshold is something that we must do. So today I didn't have time, but DataVisor actually have product to automatically suggest rule tunings so that remove the manual overhead of finding the pivot tables and calculating the threshold. So that's something that our client finds very useful in terms of automatically make some suggestions on the rules. And then supervised machine learning is also baseline to detect known fraud patterns. It works very well when the labels are complete and the feedbacks are generated quickly. So we really, for supervised machine learning, where we really want to streamline the feature engineering. I don't know whether there is a data scientist actually in the audience. For supervised machine learning, one of the key things is that when we build those features, data science are very, very creative. They build those features. When we develop models, we need a point of time simulation of that features on that transaction, because we cannot do a batch way. You actually, for example, looking at some graph patterns, at the end you find, oh, this is a pattern, but then you apply to every single transaction before that. But this way it doesn't work in real world, because you are kind of taking the subsequent information back. It's a little bit cheating and it won't work in real world. So what it's critical is that we do a point of time simulation of the incoming traffic, calculate all the features and use that feature, the dump to train the model. And then when going live, we also need 100% fidelity. What we develop for the model is what we actually going online. In many cases, we heard clients have difficulties when data science develop very fancy feature, but the IT department implement is not to the point, or it's not able to keep up with the time of computation in time. So those features don't behave very well in reality. So that's actually really, really important for the feature trainings. If you need help, DataVisor have tools to help that as well. And then we talk a lot about unsupervised machine learning already. It's really designed to capture new fraud attacks for the advanced criminal rings, and then especially useful when the labels are not complete or heavily delayed, or we actually apply to new scenario where you don't have any labels at all. So it depicts new fraud rings, and it also able to visualize. I wasn't able to show the UI today, but capture the ring and visualize it, like the example that I showed, to get organized in the way that different transactions, different users, how they look, and visualize the connections. That's very, very important for the manual investigation team to understand the attack pattern. And finally, it's very important to put everything together into ensemble. You can use actually another machine learning logistic regression to put everything together, supervised machine learning score, unsupervised machine learning score, scorecard score, or you actually can pretty much just use a simple scorecard to put things together. So then you have intuitive way to understand what's going on, why we actually detect this thing, and then more importantly, capture the reasons of the supervised machine learning. What are the fraud indicators for unsupervised machine learning? Visualize the rings so that people can make better understandings. I know there's a question.
Yep, there's one question we have. How does the precision of SML compare to UML after 6 months if no model retraining has occurred? I guess this is the question about decay of the models.
Yeah, so decay of the models, usually the unsupervised machine learning, people actually sometimes have a little bit misconception feeling unsupervised machine learning is like abnormality detection. It's not accurate. But to the contrary, it's actually not true. We often find unsupervised machine learning be even more precise than supervised machine learning, because it's capture a fraud ring. So you need to have a ring of it to actually capture it. So then to give high confidence, this is actually correlated. So in the 6 months, the supervised machine learning decays and unsupervised machine learning are usually quite robust in terms of the performance, because it's not too much associated with the retraining. And of course, as the time move on, the unsupervised machine learning will even become more like a stable than when compared to supervised. But typically people for supervised machine learning, they retrain the 6 months mark or a year mark. So I think many financial institutions are now doing the 6 months, and then if not even faster. So that's actually quite normal because they need to keep up.
Fantastic. Phong, that was terrific. I think in the interest of time, seeing as we're at the top of the hour, we might want to if there are no more questions, we can wrap things up.
Yeah, I think this is the last slide, so we are done.
Perfect.
And
So
that's actually perfect for timing.
Great. And then if you wanted to go to the next slide, please. So for those people who would like to learn more about this topic, in addition to the wealth of information that Phong has provided in the past hour, here are some resources. Of course, you can visit our website, datavisor.com. I referenced a report from Gartner at the beginning, the Buyer's Guide for Fraud Detection in Banking from Akif Khan. That's on our website, and you can access it by going to the resources section of our website. We did a webinar 2 weeks ago with Hao Lee, who is our VP of Customer Success at DataVisor, and that was titled "The Keys to Building a Good Fraud Strategy." And like this webinar, it was very strategic, but detailed at the same time, and provided a wealth of information. I'd recommend you take a look at that on our website. We have published a dummy handbook on machine learning for fraud detection. That's another terrific resource. And of course, I would recommend keeping an eye on our blog, datavisor.com/blog, because people like Phong, people like Hao, people like other people in the company are always sharing their expertise via the blog. But maybe one of the very best ways for you to learn more about how unsupervised machine learning and supervised machine learning can be beneficial is to request a demo. And you can go to our website and click on that button and have one of our experts spend time with you. It may be just as few as 15 minutes if that's what you can spare, or it could be longer, it could be a full hour. But I highly recommend that you take advantage of the availability of our experts. Next slide, please. So just to wrap things up, I always like to promote our next webinar. We're doing these webinars on a fortnightly schedule every 2 weeks. And so our next webinar will be on May 3rd, the same time, 8 a.m. Pacific, 11 Eastern. And the subject of next webinar will be ACH fraud. And the title is Fight Back Against Crime: Your Guide to Defeating ACH Fraud, with presented by Brian Pramoff, our Director of Customer Success, a brilliant guy. Again, only brilliant people can work at DataVisor, right, Phong? And Brian is certainly very brilliant. So we highly recommend, if you can free up some time, that you join us again 2 weeks from today, same time, 8 a.m. Pacific. Next slide, please. So that brings us to the end of our webinar. Phong and I would both like to thank you very much indeed for spending the past hour. If you stuck around till now, we really appreciate it. We know you're very busy, and there's a lot of ways you could have been spending the past hour. So if you've chosen to spend them with us and stayed around for the full hour, as most people have, we truly appreciate it. We hope to see you again at another webinar in a couple of weeks, or you can reach out to Phong or myself here. We're sharing our email addresses, and we'd love to hear from you. But for now, that's all we have time for. Thank you very much for attending. Thank you, Phong. That was a fantastic webinar. I learned a lot. Great presentation, and I'm sure the audience benefited from it too. So that's all we have time for. Thank you very much. Bye for now.
Thank you all.